Hello, welcome back. So we've been talking about this idea of interactions all semester, and in the last video we were talking about what if the interaction was happening with an object that wasn't a solid. It's not really something we've looked at so far this semester, but we do know other phases of matter exist. We have solids, we have liquids, we have gases, and amongst those we consider liquids and gases to be fluids. And that idea of fluid just means like this object flows, right? This material flows in the typical sense. And yeah, we have a better physics definition involving shear forces, but for us, it's good enough to say an object flows. And then we say, well, an object that flows can be compressible, it can be incompressible. We consider liquids, generally speaking, to be incompressible, and gases, generally speaking, to be compressible. And there are gases that are considered incompressible and liquids that are considered compressible, but we're not going to deal with those. It's another story. And as we get to discussing these different phases of matter, we have to really start to comprehend how interactions happen among surfaces, because surfaces are going to be a very important topic when we talk about fluids. And when it comes to surfaces, we describe interactions, yes, with forces, but a better definition of an interaction with a surface would be a pressure. And the goal of today in this video is to really figure out, how can we define this pressure and why might it be useful? So jumping into the topic, we have two goals. Again, defining this pressure and, what is the SI unit of pressure, and explain how force and pressure are related. Those are two main goals. Now, in essence, we define pressure with a capital P. Pressure will be dependent on a force, and we'll use F for force. And here's another key term for today, A for area. Now, again, I give you these values. I'm making it clear up front. What do I mean by each letter? P for pressure, F for force, A for area. And the reason why I do this is because I want to make sure that we do not mistake P for rho, that is density. That is going to be an important part of our discussion. And I also want to make sure, we don't mistake P for momentum. Momentum we use the letter P as well for. Also, remembering when we talk about capital A, we are not talking about acceleration. We are talking about the area. So just keeping our terms in order, and F we've used for force all semester long, so that should be fine. So what is pressure? Well, pressure is a description of interactions, but it specifically removes this idea of force and talks about what results from an interaction in a sense. If we take, for example, a force and we apply it onto a large area on your arm with a finger, well, that finger that we're pushing against the arm with, that finger's not going to pierce through the skin. However, if you apply the same force in a needle, well, that does pierce the skin. And the reason why is because when we talk about interactions, what really matters here, as far as the result of, will the needle pierce the skin or not, the important factor here is this idea of pressure, how much pressure is applied. We say like skin can withstand a certain amount of pressure. So when we talk about interactions with surfaces, such as the interaction with the surface that is the skin, we get a different behavior whether we apply it over a large area or a small area. And in general, we say, well, the pressure is going to be what? It's going to be inversely proportional to the area, right? A small area gave us a large change. Here, that large change is a result in piercing skin. And a larger area, as is the case in picture A here, the larger area resulted in less change in our physical system. The finger's not piercing the skin, in other words. So you say pressure is proportional to A. However, That being said, if we imagine this force gets large enough, well, certainly if the force gets large enough, it can do some damage, right? It can certainly hurt the person if we push hard enough. And that is an indication that pressure, well, it depends also on this amount of force. So you get that pressure is dependent on the inverse of area, and pressure is dependent on force. And we combine these together to get the idea that pressure is going to be force over area. And sometimes you'll see this as a vector, that the pressure is in the same direction as a force. Sometimes we consider this a scalar, and I'll discuss why we might consider it a scalar in the future. But for the purposes of this class, we will, for the most part, consider this just a magnitude of pressure. We'll figure out directionality of the force through context clues. So we have this idea of pressure. What is pressure? Pressure is a description of an interaction between or acting on a surface. And pressure is related to how much force we apply on that surface. And it's also related to the area of contact on our surface. So we then ask the question, well, the needle and arm, that's dealing with solids, right? I said we're moving into this realm of talking about different phases of matter. So how does this apply to a liquid? When we think about a liquid, or a fluid more generally, fluids exist in containers. And with our container, we could look at the bottom area and we could ask how much pressure is the liquid exerting on the bottom area of our surface. And, if this pressure gets too large, the bottom area will probably break out. So how do we discuss an interaction with a fluid? Well, we see how does it interact with the surface of the container. So inherently what we're looking at is pressure. We want to know what is the pressure on the bottom area because that'll tell us about how the fluid and the container are interacting. Well, pressure is defined to be force over area, right? What is area? Well, area is the area of contact. Here it's the entire area of the bottom surface. What is the force? Well, what is causing that pressure at the bottom? It's all of this fluid. So we want to figure out what is the pressure on the bottom. Well, it's due to the force of the fluid pushing down. What's causing that force? Well, it's a gravitational force of the earth pulling down on the fluid. If we were to draw a free body diagram where we say this dot represents the fluid, the liquid inside of this container, that fluid would have a weight pulling downwards. The weight, because fluid exists on Earth, it does have weight. The weight described by mass times acceleration due to gravity, where m is the mass of our fluid. And we have an upward force. What is that? That's the normal force. That's the surface pushing upwards. That is the force being exerted on our fluid. So if we look at the pressure on the surface, well, it's going to be related to this normal force. What do we know? We know this fluid isn't moving, so the normal force must be equal to the weight. So we can write the pressure as mg over area. So we have this definition of force that depends on mass, it depends on area, but we can go a little bit further here. How can we go a little bit further? Well, we could go a little bit further by looking at this fluid and say, well, this fluid has some mass, it has some volume. We can define a density. That density, which is mass over volume, right? We went over that in the last video. And when we take this, we can look at our container, and a cylinder will have a volume of area over height. So we can say mass divided by area times height. So we just replace our volume with area multiplied by height. And we rearrange this. And you'll see why we want to do this in a second. We rearrange this to say mass is equal to density times area times height. And when we do that, we can replace the mass in our pressure equation to give us density times area times height times g over area, right? We're just replacing mass with density, area, and height. When we do this, we see, oh, well, the areas cancel out. And we get that the pressure is equal to the density times the height of our fluid times the acceleration due to gravity. And this is interesting. Why is this interesting? Well, it's interesting because it doesn't actually depend on the area of our container's bottom. There's no area in our final term. It doesn't show up anywhere. It only depends on the height of the surface of our fluid, and it only depends on the density of the fluid, meaning what fluid is present. And then we ask the question, well, can we be maybe a little bit more specific about this? If we look at our pressure, we can define our pressure to be 0 at the surface. And if we look at distance h downwards, not at the bottom of our surface, but we look at distance h downwards and we ask, well, what is the pressure at this position? And this might seem like an odd question. What do you mean, what is the pressure at this position? Basically, it is asking if I were to place a surface down at this location, not the bottom surface of our container, but place maybe a disc or some object down there, something that has a surface. If I place it down at this distance, negative h, go from 0 to negative h, the negative indicates downwards, right? If we were to do this and ask the question, what is the pressure that a surface placed at that location would feel? Well, just like last time, we had rho g times h, where h is our distance below. And this is to say that this pressure gives us the pressure at any location inside of our fluid. So if we put an object down there, we can make a prediction about how it's going to behave. But that relies on defining pressure to be 0 here. And that's actually a problem. Why is that a problem? That's a problem because there exists fluid above our container, right? Above our fluid, above our liquid surface, there exists fluid, the atmosphere, right? The gases that's around us. So really what we would want to do is define P naught, not to be 0, but to be what we call the atmospheric pressure. And this is a known value. You can look this up. Depending on where you're at, you might get a slightly different pressure depending on elevation. But this is your atmospheric pressure. So really, what we would want to describe this pressure as is equal to rho GH from our fluid, from our liquid, and then adding to that the atmospheric pressure. And this is what we would call the absolute pressure. We'll get to a discussion on why we call it absolute pressure and how we differentiate it from other types of pressure. But this gives us a value for our absolute pressure, we call it. And it does include this idea that the atmosphere is above it. Now, I do want to take a quick look at the units, right? We look at pressure. We say pressure is rho GH times pressure atmosphere. That means the units of pressure, use square brackets here for units, is going to be, well, density will give us a unit of kilogram per meter cubed in our SI units. Take a look at acceleration due to gravity. That's going to give us units of meter per second squared. And we look at h, and h will give us units of meters. We do some combining here. And what does this give us? Well, one of our meters is going to cancel out with one of our meters here. So that'll give us, let me do some erasing here. So what'll that give us? That gives us a kilogram meter per second squared times meter squared. And I'm intentionally not canceling out one of my units of meters here. And looking at this kilogram meters per second squared, we've seen that before. That is how we define the unit of Newton. So we say the unit of pressure therefore must be a Newton per meter squared. What do you know? That's a force divided by an area, as we would expect. And this is your base SI unit of pressure. All right, so going back to our goals for this video, right? Define pressure. What is pressure? Pressure is the interaction that occurs at a surface of an object, and we can look at that interaction as being, yes, between two solids like our needle and our arm, or we can look at it as a pressure from a fluid acting on a surface. And that's really what's going to be useful to us moving forward. What is the SI unit of pressure? That is a Newton per meter squared, which tells us the relationship for pressure between force and area is that pressure is going to be inversely proportional to area, proportional to force, giving us the relationship that pressure is force over area. All right, so that's a rundown of pressure, right? And in the next couple of videos, we're going to start looking into how to utilize pressure. So looking at more of the application aspect. Thank you so much for watching, and if you have questions, please ask, and I will see you later.